Welcome mechanics and materials students. In this lecture I'm going to go over a tapered shaft that is a torsional shaft. So this is from our section on circular torsional shafts. So just do a quick recap, verbal recap properties. We're talking about elastic behavior. We're talking about small twist angles that enabled us to make small angle assumptions throughout the derivation of our displacement strain relationships. We have one and only one strain, and that is the shear strain in the axial versus circumferential direction. So that's our gamma z theta direction. Everything else is zero. Hooke's law gets real simple. So our shear stress, our tau z theta, is simply going to be our gamma z theta, our shear strain, times our shear modulus for our material. And then we can compare that shear stress to whatever the material is capable of providing. So remember, when you look up your tensile yields, if you're comparing to a tensile yield, remember that you're effectively going to have to get an equivalent max shear from your tensile yield. Usually that involves dividing it by 2, because those tensile strength tests were typically done uniaxial. So whatever your maximum tensile stress that was measured at yield corresponds to half of that would be the shear stress that the material was seeing. So that's all the shear stress you want your material to be seeing in your torsional shaft. Okay, in a previous lecture, I went over a stepped shaft using examples from the Vabel textbook. And so now I'm going to do just a very quick overview of what would happen if we didn't have all constant diameters. So for this we have a tapered shaft, and this is again an example from the Vabel textbook. So you can look up all the step-by-step nitty-gritty details in Vabel. It's very good, but I'm just going to kind of lay out the basics here. So for this we've got, and this is probably not drawn to scale very well here. I think this constant diameter section was significantly short. Yeah, it was 4 times shorter actually. It's kind of tiny. Okay, so this is our axial z direction, and the radius in this constant section is basically r, so we'll call it, it's a constant multiplier. And out here at the very end, it's 4r. And so everything is in terms of some index. So basically we can scale this. This would be something great. You could write your relevant equations into a spreadsheet, and then you could scale everything up and down by r. So this was a design that is say scalable if maybe you were manufacturing these in an assembly line or whatever, or making them to order, different scales in your NC mill. So here's our different z lengths. So in our stepped shaft, these would have been the lengths that would have corresponded to different radii. In this case, rather than having single radii within each of those sections, we've got one where the radius is in fact dependent on our position axially, because it's a tapered shaft. In fact, it is dependent linearly. So we can make a little equation based on a particular position down the shaft. If we said the end of the shaft here represents z equals 0, we could write an equation for the radius at any point z, and we would find that equals 4r, which is a constant, basically for any given r, minus 3 divided by 40 times z. So it's linear taper. Had it been some other kind of function, had this been parabolic or whatever, we could have found that function. That function is probably something that somebody would have had to program into a milling machine, or if they were making this by additive manufacturing, it would have been something that you would program into your coordinate additive manufacturing machine, whether it's in this case probably laser sintered because it's torque converter, so it probably has to have a little bit of strength. But regardless, this very equation is something that you could use in fabricating this item. So chances are you know what it is. And out here, of course, the radius is r equals constant, r equals r. Okay, this z-dependent radius is going to be felt, so to speak, in our expression for IZZ, and basically any expression for tau, because tau loops back and has an r factor within it. Otherwise, we would treat this problem finding twist rate and finding angle of twist at any given point along the shaft exactly the same way that we would in a straight constant radius step shaft. So the first thing we need to do that, like right now, there's no angle of twist and there's no stress and there's no strain because there's no applied loads. So let's start out by applying some loads. And we don't know how much load we're going to apply, but we're going to scale it by some factor t for torque. So we're going to apply a torque t kind of in the clockwise direction if we're facing down the z-axis, out there at the end at 50, z equals 50r, and we're going to go the other way to the tune of 2.5 t at 40r. So that means over here at our base fixture, which is, it looks like it's welded into a wall in the Vabel figure, we're having to have a support reaction again in the clockwise direction of 1.5 t. Okay, so from that we can kind of do our torque diagram. Again, this is equivalent of our shear and bending diagram, and that we're all familiar with from statics. So here's our z and our internal moment. So we have a positive. If I'm going down the z-axis, I'm applying a positive 1 point t. So if I section the shaft here, that I would have to be applying a negative 1.5 t to keep that cut end in static equilibrium. And then at this point, I have another externally applied torque to the tune of 2.5. So if I made a cut here, I would be opposing 1.5 in the clockwise, minus 2.5 in the counterclockwise. So I would have to basically be providing 1 t here in the clockwise, which will basically be satisfied by our final applied. So here's my internal moment. So I've got basically t and 1.5 t, and those are constant. It doesn't matter what the taper of the shaft is. The taper of the shaft only determines stress and strain, which in turn determines twist and twist rate. But basically my applied loads are determined by position and basically static equilibrium. Even if I'm cutting the shaft and I'm looking at internal loads, they're still loads. So they're not stresses. But I do know what they are. So now I can work backwards and start finding things like twist rate and shear stress. Those are the two things I'm going to care about here. So let's get another color. Let's do green for twist rate. So going back to our handy equations for twist rate, and in terms of, in this case I'm going to do one in terms of moment, reminding myself. So applied moment over any section, and you can look these up. It's going to be my polar moment of inertia times my twist rate in that section. Okay, so these are going to be specific to my z position. my M is going to be specific to the zone I'm in basically, but my IZZ is itself going to change with each different increment I move in the Z in this tapered section. So the dependence now of this taper is going to be felt through my IZZ term. So if I'm looking at this first section in the tapered section, let's look over here, let's just say tapered section. So Z goes from 0 to 40R. I have my moment is 1.5 times T, and that's going to be equal to whatever the shear modulus of my material is times IZZ. It's still a circular cross section, so I can say that that's equal to pi over 2 times r to the 4th times whatever my twist rate is, d theta dz, which I'm probably going to want to solve for. Okay, so r to the 4th is my r as a function of z raised to the 4th, which is basically my line equation for r minus 3/40 z all raised to the 4th. So if I were to write my twist rate tapered section, I would find that it is basically, I just do a little algebra here. I end up with my moment on the top, which I'm indexing to some variable t to scale. I got my shear modulus on the bottom. I got a pi over 2 term. And then I have this, basically the taper profile, which again, we've said it could be anything. In this case, it's a linear function of z, but that whole term is raised to the 4th power. Okay, in a non-tapered profile, say, where say you had a straight shaft, there wouldn't be this z term. There would be this. There would be a constant r, and so we would say that the twist rate is constant, is not changing. So the angle, you're going to have so much of a step around the shaft for every step up, a constant pitch in terms of our rate of twist. In this case, the very fact that we have a linear taper, we're going to end up with that IZZ on the bottom. We're going to end up with a 4th power of z. So the rate of twist is now proportional to the 4th power of our position down the shaft. So, excuse me, if you think about it in terms of how quickly we're beginning to gain additional radians of twist, when z is really small, this term basically is large. It's in the denominator, so that makes the twist rate small. But when you get out over here, basically for every increment you go over, you're getting a whole lot more radiance. And if you think about it, you can think about moment of inertia as resisting strain, just like it resists acceleration. It's kind of a one-to-one with dynamics. So you've got your moment at the top. The bigger your IZZ is, basically the smaller your angle of twist. That's related to strain. Basically, if you were in dynamics, we would say it's a smaller alpha. So basically we're changing our moment of inertia smaller as we move in the positive z direction. The taper could have been going the other way, in which case it would decrease as we go forward. So if we want to add this up now and say, well, okay, what's my delta theta as I go from z equals 0 at the wall to my 40r where I have that junction, basically I would just integrate this with respect, this side with respect to z. So I would end up with the integral from the angle at z equals 0 to the angle at z equals r times 40 d theta, which gives me my delta theta, equals the integral from z equals 0 to z equals 40r of, let's move all the constants out of the integral. It's going to be a crowded integral in there. Let's do 3t over pi, doing a little algebra there with my t and g as constant. We're not going to change the material as we go down the taper. When would that change? The times you could get a continuous change down the material, it is very unlikely for shear. The only thing I could think possibly might do it would be some kind of gradient reinforcement composite. And even then, I'm not quite sure how you'd lay it up. So I think it's pretty safe to assume we can, G is constant, our shear modulus, we can pluck it out from the integral, inside the integral, and we're left with our 4r minus 3/40 z to the -4 dz. So we can integrate that as we need over our r and get our delta theta, plugging in our limits of integration. And again, this is in the Vabel textbook, so you can basically, I won't walk through the math. I'm just setting you up to do that. If you want to get the total angle of twist at the end, we basically go through piecewise integration. And what we would do is we would get our total twist angle from z equals 0 to 40 from this expression. Then we would pick up, we would basically add the twist angle that we get for our second section. So we will have a different twist rate. So if we go to the straight, in fact, let's get another color here. We're going to go to the straight. It's going to be a little bit lighter. So if we go to the straight section, our twist rate is going to be a little bit simpler. We're going to have, first of all, we're going to have a lower torque or a lower internal moment. Let's say internal moment. We don't really care what the applied torque was. We took care of that up here in this red diagram. Now we care about the internal moment, which is in this case 1t. We got the same. We're assuming we haven't changed materials. We still have a circular cross section, so we have pi over 2. But this time we have a constant radius. So our moment of inertia expression is just going to have the radius for that section raised to the 4th power. And this is all a constant. So our twist angle change as we go from basically from z equals 40r to z equals 50r to get to that end of the shaft is just going to be basically 10r times t divided by g pi over 2 r to the 4th. So we can do some simplifying. So it would basically, we did a head integral, integrated a constant, and just multiplied by our change in z right there. So we would add this basically to this. Now there, because t, we could basically say, if we're saying that this is a positive 1.5 because these are different signs, we would put a negative sign. So we'd actually, if we're twisting one way in the tapered section, we're actually twisting the other way in the other, and that's simply because these are different signs. Our internal moment flips its direction as we go through this exchange point because of that 2.5 applied moment that we see right there. Okay, so that's how we find effectively what we could call torsional deflection. So we get to do a real integral because we have that tapered profile, which is giving us a changing moment of inertia as we go down the shaft. Now we're going to wind up with just a quick treatment of how about the total amount of torque we can apply. Are we going to have a problem with our material? Because we know that our material enters in our shear modulus, but ultimately we want to make sure that our tau z theta, which is the only stress we have in the material, because we're not squeezing it, and this is pure torsion. We want to make sure that this is below tau yield, which again we're going to assume is the same thing as 1/2 of our tensile yield. Okay, so what we need is to use the expressions we have, including our z-dependent moment of inertia, and get ourselves an expression for tau. And we'll just take a look at how it changes with position down the shaft for this particular applied set of torques. So we know that for a torsional shaft we can express tau z theta as shear modulus times the radius anywhere times that twist rate. Okay, so we already have a twist rate for each of these sections. Right here. Let's focus on the tapered section first because it's a little bit more complicated. And we can write R in the tapered section. We're going to write this in terms of our line. So we know that the radius anywhere we want to be in that tapered section is just our 3/40 z. And this is our 1.5. Actually, let me simplify that, 2 pi at the bottom. It's going to be 3t or g pi. And then we have our linear expression for radius in terms of position raised to the 4th. Okay. So what we basically have is one of these expressions that's in the numerator. We have 4 of them in the denominator, and then we've got shear modulus in the denominator and the numerator. So if we wanted to do some quick algebra, we could cancel that, and that ends up being to the 3rd. So our shear stress at any z position within this tapered section is basically going to be what ends up being twice the internal moment divided by pi. And then we have our line equation for radius in terms of z raised to the 3rd. So if we were looking at a yield criteria, we would want to find where is this the biggest. This is going to be the biggest where this variable term in the denominator is the smallest, and it's going to be the smallest basically where z is the biggest. So I mean, you could think of basically if this goes to 0, this term blows up and becomes infinitely large. So as z gets bigger and goes towards where we're pretty small here, this term gets smaller. So we would be looking towards this point. We would look at the 40r. So if we put in 40r for z, we would end up with a single r in the denominator, and that would allow us to calculate our max tau. Now if we wanted to check the whole thing, we would also go over here and check to make sure that we didn't have a limiting case for our shear stress in the straight section. Don't think we do, but it would be worth checking. In either case, your design would be limited by, if you were, say, making a choice of materials, you would choose this such that it would accommodate whatever the largest tau was, whether it was at the very end of that tapered section or further out into the straight section. I'm thinking it's at the end of the tapered, but definitely need to check. So that's an example of how you can apply our torsional elasticity to a different profile shaft. And again, any function of your shaft profile could be accommodated. Any continuous function that you can integrate, take the derivative of, manipulate is fine. Finite element, would allow you to literally do anything. Anytime you have a discontinuity, of course, like you do with any other mathematical discontinuity, stop, do a piecewise integral if you're adding up your angles of twist, and certainly remember the equations that are specific to any length of the shaft, whether it's because you have a certain radius profile, you have a certain shear modulus, not likely, you have a certain internal moment due to the way you've applied the torques. Those each need to be treated separately to calculate twist rate, to calculate twist, and to calculate max shear. So that is it for this. I would highly recommend that you, if you're using the VABL textbook, that you step through this in great length. There's a lot of detail there that you can go through. And it's a very good fundamental treatment of variable input parameters, which is something that those of you who will go on and use things like COMSOL multiphysics and other types of powerful analysis programs, the ability to visualize your input variables as functions as opposed to just numbers is something that will give you a lot of flexibility. So enjoy. And we'll see you again for some discussions of beams if that is the next section, probably the next section in your course.